All right, so today we're looking at dot product and vectors. Remember last time in 6.1 we did a very basic introduction to what is vector notation, how do you add and subtract vectors, so we did pretty basic stuff. Today we're looking at dot product, which is the multiplication of two vectors. That's a little bit different, and then projection as well. Okay, so the dot product is also called the inner product sometimes. But basically all that you do for the dot product is you take the first two components of your two vectors, so the x components a times c, and you add b and d, or b times d. Some special cases are if you take the dot product of the same vector with itself, it's actually the same thing as taking the magnitude squared of that vector. We'll do an example where you'll see why that works out the way it does. The other special case is if you have a zero vector. Notice that this is bold and this is not. Bold means vector. The zero vector means basically a vector where both components are 0. So that's why this works out, is if I take the 0 vector and I dot product it with another vector that has actual values, that's going to be 0 times a, right? Plus 0 times b, but what's that going to equal? The real number 0, right? So make sure you're paying attention to that difference in notation. 0 vector times b is going to equal the real number 0. Okay? So let's see how we take a dot product. Pretty basic computation if you know it. What is my computation going to be here? So don't tell me the actual answers or the answers along the way, but what am I doing? Multiplication of, what's the first multiplication I do? 10 times 3, and then I add -1 times -7. Yeah. Now you guys, as you get comfortable with this, you can go straight into saying 30 plus 7. I do need to at least see those two numbers. I know that you can do it in your head and go straight to the number, but I want to make sure that I see how you're getting there. So at least show me this step, and then you can say that that is 37. Easy enough? Easy enough. All right. So another interpretation of the dot product would be the geometric interpretation of the dot product. Okay, so we come up with the multiplication of two vectors actually by using the law of cosines. All right, so the way that we do this is we form a triangle, and we do that. Let's see if I can do this here. By connecting the two heads of the other vectors that we're looking at. And name that vector, well, we'll call it v plus w, but let's call that vector, I don't know, what do you want to call it? Epsilon. I'm going to call it s for some. Sorry, I know I asked and then I didn't like it. Epsilon seems like a weird thing to use for this. All right.
What does it sound like?
What?
What does it sound like?
I didn't say it sounds, I said it just seems like a weird thing to use.
Oh, I was like, what?
All right. So what I'm going to do here is, using the triangle, I'm going to write the law of cosines out with that angle theta between the two given vectors. All right. Law of cosines says that the distance of the opposite side, and remember the distance of this opposite side happens to be s, magnitude of s, right? squared equals magnitude of v squared plus the magnitude of w squared. Whoops, I wrote that backwards. Minus two times v times w times the cosine of theta. Okay. Where do you think I need to go with this? What is S? S is actually just the multiplication or the addition of v plus w, yeah? And I probably could have just written that in the first step. I probably didn't need to. Do the other thing. Okay. If I were to square that whole thing out, I would get v squared plus v dot w plus w squared, or 2v dot w, sorry, I need to go back. And that would equal, in v squared, remember that on the last slide we said the special case was that if you take the dot product of a vector with itself, it's the same thing as the magnitude. So technically on these two terms, I don't need to have those magnitudes written on. Same thing on the other side. And now you can see the v's cancel, the w's cancel, and I'm down to 2 v dot w equals, oh shoot, hold on one second. I messed one thing up. Do you guys see what it was? Look at the vectors. How do I add vectors? Do I connect head to head? So that's technically not addition, that's technically subtraction. Yep. So I didn't catch that on my first go around here. So that should be minus, which changes this part to a minus, right? Minus, minus, which leaves a minus. And now we can see that if I divide by -2, I lose those, right? The -2's. So that means that v dot w is also equal to the magnitude of v times w times the cosine of theta. So this is another interpretation, another formula I can use for the dot product. The magnitude of each vector multiplied times the cosine of the theta in between. So that's the more complicated theta. This is the one you'll use if I'm asking about an angle or if I give you an angle and some magnitudes. This will be the formula that you use instead of that algebraic one that we just did. Okay? It can also be used for this type of a problem. So it says to find the angle between the two vectors. What I can do to find the angle between the two vectors here is use that last formula. So I can calculate the dot product between the two. Set it equal to the magnitude. What is the magnitude of u? How do you find the magnitude? Pythagorean theorem stuff. So the square root of 5 squared plus -12 squared That's the magnitude of u. I want to multiply that by the magnitude of v, which will be 4 squared plus 3 squared. And then that times the cosine of theta, right? So now I need to go through and calculate all this. For the dot product, I've got 5 times 4 is 20, plus negative 12 times 3 is negative 36. That's going to equal, I'm going to solve these square roots down a little bit. 5 squared plus 12 squared is 169, square rooted is 13. 4 squared plus 3 squared is 25. Square rooted is cosine of theta. So then 20 minus 36 is negative 16. 13 times 5 is 65. And now I can start getting close to isolating that theta. I'm left with the cosine of theta is equal to negative 16 over 65. And at this point, I can use my calculator. So can somebody with a calculator please tell me if you were to type in cosine inverse of negative 16 over 65, what do we get?
104.25.
And there you go. You can use this same formula if instead I gave you what theta was and then I gave you the magnitudes of u and v, then you could figure out what the dot product is as well that way. So there's a number of different things I can give you with that formula and ask you questions on how to use it, right? This is just one of them. All right, so this one says to find the magnitude using the dot product. Remember I told you that the magnitude squared of a vector, oops, sorry. So I had told you that the magnitude squared of a vector was equal to its dot product, right? Which means that the magnitude of a vector is equal to the square root of the dot product. Now think about that. When you do the dot product of something, so I've got square root here, and if I take the dot product of 7, negative 3 with itself, don't you end up with 7 squared negative 3 plus negative 3 squared? So that's why it's the same thing. I mean, it's all the same computation. It's just a different way of writing it in the sense of notation. But essentially, here we're still going to end up with 7 times 7 and then plus negative 3 times negative 3, which would have been our Pythagorean theorem anyway, right? So then this is the square root of 49 plus 9, which is the square root of 58. All right. So here's where things start to get a little bit more fun. We have orthogonal vectors. So orthogonal is two vectors such that the dot product is 0. Okay. Think about if the dot product is 0 really quick. I'm going to write something off to the side so you can kind of think about it. If you have that a vector u times a vector v has a dot product of 0, and remember that dot product is supposed to equal the magnitude of u times the magnitude of v times cosine of theta, right? What's the only way that you're going to get 0 here? Is if one of those pieces is 0, right? So either the magnitude of u is going to equal 0, or the magnitude of v is going to equal 0, or what else could equal 0? cosine of theta could equal 0. All right, if the magnitude of u or v is 0, what does that mean about that vector? It's a 0 vector, right? That it doesn't exist, really. What if the cosine of theta is 0? What do you get from that? What would theta have to be? Pi over 2 or 3 pi over 2, right? So 90 degrees or 270 degrees, which means what about the lines? Perpendicular vectors, right? So that's what can happen. When you say that two vectors are orthogonal, it either means that you are dealing with a 0 vector, in which case you don't even have a vector in one direction, right? So can they be perpendicular in that case, if it's a 0 vector, right? Or if you have two non-zero vectors that are getting a dot product of 0, then you know you have perpendicular vectors, right? If both of them are non-zero. All right, so that's kind of the analysis of that. Let's take a look over here. It says we want to find x so that the two vectors are orthogonal. So basically, you know that you want the dot product to equal 0, right? That's your setup, is that you want 2, 3 dot product with negative 7x. We want that to equal 0. So if you calculate that dot product, you get negative 14 plus 3x equals 0. And then you can just easily solve that for x. And you're done. You'd have to know what orthogonal means, though. So the whole reason why I went through this over here is because you guys probably have heard about orthogonal in physics if you're taking physics. And a misconception is that it means that the two vectors are perpendicular, right? And yes, that's true most of the time, but I did need to point out that it could also mean that you just have a 0 vector, right? So watch out for that. It doesn't guarantee that you have two perpendicular. It just means that the dot product is 0. That's the computational meaning of it. All right. So the last concept, and we'll do a couple examples with it, is the projection vector. All right. So you can see that the way I'm reading this is the projection of a vector w onto another vector v. So whichever vector you are projecting, you are essentially taking a line from the end of that vector and dropping it perpendicular to the vector across from it that you're trying to project onto. So I would be looking at taking a perpendicular line from v down, or from w down to v, such that it forms a right angle. And then the projection vector is actually the vector that's, oops, let me draw that a little better. It's the vector that is still in the direction of v, ending though with a different magnitude now, ending with the magnitude where that projection dropped down to. This right here is your projection of w onto v. Yeah?
Is there a different notation to write that? Like just saying like projection?
Not that I've ever used. There might be, but... So, yeah, he's looking at the notation here, and make sure that you're reading this correctly. The upper letter here, so the letter that's on the normal plane, tells you which vector you're projecting. The subletter tells you which vector you're projecting onto, right? And you want to be keeping the direction of the vector you're projecting onto. So that's why v is used mostly in that formula, is that you're trying to maintain the vector of the one that you're projecting onto. Okay? So the formula is to take the dot product of the two divided by, and remember this is essentially the dot product of v times v, right? Or you can think about it as its magnitude squared and then times v. V being the vector that you have dropped onto. Okay, so let's look at a couple examples. So for this one, it says find the vector projection of u onto v, then write u as the sum of the orthogonal vectors, one of which is the projection of v on, or u onto v. So first things first, I'm going to draw a picture so we can kind of see what's happening here. So you can see these two vectors are primarily in quadrants 1 and 4, primarily, right? So I'm going to draw that. And I'm just kind of guesstimating, so this isn't going to be perfectly to scale, but I'm going to do the best I can here. The vector that's going from 7 to negative 5. So let's see if I can tick this up decently enough. 1, 2, 3, 4, 5, 6, 7, down to negative 5, negative 1, 2, 3, 4, 5. So I've got a vector going, kind of looks like to about right there. And I've got a vector going to 2, 1, right? Which is going to be about right there. This vector on top here is my vector v, and this is my vector u. So which vector am I projecting onto? I'm projecting onto the shorter, meaning that I want to start at the tip of u and draw a perpendicular line down to v. Now notice that if you look at the, like if I were to start trying to draw a perpendicular line from u to v, does it look like it's, am I going to be able to connect directly onto it? No, I'm going to have to kind of extend v out a little bit. So what I'm going to do is make a dashed line to extend this out so I have something to drop onto. Okay? So for the projection part, starting at the tip of u and then going down to perpendicular about as good as I can, right there, right? Now that's just showing me where I want my projection vector to end. Remember that my projection vector is actually still on which vector? It still is on v, right? So my projection vector technically is this one right here. Everyone see that? How do I calculate that vector? What do I do? So notation-wise, I'm going to write that I am looking for the projection of, and I'm projecting, so if I'm projecting u, is u the subletter or is u the in-text letter? Yeah, u is the in-text letter, and v, if I'm projecting onto v, then v is my subletter. The formula for this is equal to the dot product of u times v over which vector am I using on the bottom and for the rest of the problem now? V, the one that I'm projecting onto, right? So now I'm going to do v squared times v. All right. What is the dot product of u times v? And you don't have to write it all out, so you can just kind of look here. It's going to be 7 times 2, so that's the one I did want you to write out, is 14, plus, and then what am I adding or subtracting? Plus a negative 5, right? That's the dot product. All over, what's the magnitude of v? It's going to be the square root of 2 squared plus 1 squared, but then I have to square out that whole thing. And finally, I'm going to take whatever that number ends up being, and I'm going to multiply it by the vector v, which is 2, 1. All right. So 14 minus 5 is 9. I'm losing my square root on the bottom because I've squared it, so it's just going to be 5 times 2, 1. That ends up being 18/5 9/5. So this is my projection vector right here. All right, the next part of the problem said that we wanted to find, or we wanted to write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So that sounds confusing, but take a look at the picture, right? Here is u, and I'm trying to find two vectors that are orthogonal that add up to u, where one of them is the projection. So here's the projection. Notice that this green line right here would be the vector that I would want to add onto it, right? Heading in, and the main thing we have to put on that I haven't already is which direction I want to have that go, and this is the direction I want to have that go, right? Now remember that if you know 2 points on a vector, you can just do the heads minus tails rule to find out what that vector is, right? So what I'm going to do really quickly is write out what the points are. What is this point right there? What are the coordinates of that point? Nope. 2, 1 was right there. Yep, it's the projection points, right? 18 fifths and 9 fifths. Is this the head or the tail of the green? Tail. This is your tail of the green, right? So what is the head point of your green? 7, -5, and that's your head point. So if I'm trying to find this green guy, I am just going to use the heads minus tails rule to find that. Oops. I don't know why I just lost that. Okay. Heads minus tails rule to find the green. So I literally take my head point, which was 7, -5, and I'm going to subtract the tail point, which was 18 fifths and 9 fifths. Okay? What is 7 fifths, or 7 in terms of fifths? So 35 minus 18 is 17 fifths. -5 in terms of fifths? -25 minus, or plus, yeah, minus 9 is going to be -34 fifths. And so that would be one of those. So basically what my final answer for this part is that u, my vector u, is equal to the vector 18 fifths, 9 fifths, which is my projection vector, and then plus 17 fifths, -34 fifths. Are there any questions on that? Oh, sorry, I didn't realize that went into the dossier. Hopefully you can read it okay. Yeah.
Wait, so are they orthogonal because of the projection?
Yeah, they're orthogonal because we always draw the projection to be orthogonal.
Okay.
Any other questions on that? No? Okay, one more problem, I think. All right, so for a given line, we want to find the x-intercept and the y-intercept. Well, that should be easy, right? Starts out okay. Then I want you to find a point P so that the vector v from A to P is perpendicular to the line and such that the magnitude of that vector is 1, so that it's a unit. Okay, so let's start by drawing a picture of this thing. Sorry, I was pausing. I don't know why I paused for so long. And let me try and draw that a little bit bigger. Okay. And actually, do I need to have that much of the graph showing? What is going to be my x-intercept? 7, and my y-intercept is going to be -3, right? So I probably don't need to be drawing my graph that far over. I can probably draw it kind of more this way. Well, like that. Okay, so we said that the x-intercept was 7. How did you guys find that? You plug 0 in for the y and solve, right? So if you plug 0 in for the y, that essentially gets rid of this term. Divide by 3, we get 7. Okay, to find the y-intercept, we plug in 0 for x, so that gets rid of this term. Divide by -7, that leaves you with -3. So that's how we found those. All right. So then we want to draw the line that runs between those guys. Good enough. Got a little low, but you guys got the point. All right. What did I say was point A? Which point? Yeah, so this is your point A right here. And I want you to find a point P so that so that the vector formed from P to A, or A to P, is orthogonal or perpendicular, right? But it has a magnitude of 1. So is it hard to find a line that's perpendicular to that? Shouldn't be. What do you know about, how are you going to find a perpendicular line? It's just the what? Opposite reciprocal, right? So what is the slope of this line right here, of our given line? What's that slope? Rise 3, run 7. Back to algebra 1 we go, right? All right. So if I wanted a perpendicular line to this, what do I know I want my slope to be? -7/3, right? But the problem is that if I count out -7/3 from that point, which I can definitely do, so I can rise 7 here, and I need to extend my axis a little bit if I'm going to do that. So if I want to rise 7, and run 3, then that's going to take me to that. Oh, I didn't give the point, did I? I'm working on it. All right, so it's going to take me, if I'm going to rise 7 up to here and then run back 3, it's going to take me to 4,7, the point 4,7, right? Why is it not making the point? There we go. All right, so in other words, the line going through, whoa, not like that. The line going through these points is perpendicular. But does it have a magnitude of 1? How do I find that point that's going to have a magnitude of 1? But remember, unit vectors are always formed off of where is a vector form always drawn from? From the origin. Is my point at the origin yet? Could I technically relocate this line at the origin and then scale it down and move it back? Wouldn't that be pretty easy? The only other way to do this really would be to somehow try and use the distance formula, but that sounds like a big headache to me, right? So what I would do is take this line, shift it this way so that we count out that slope off of the origin instead. So in other words, count out rise 7, run 3 this way. So in other words, looking at this line, pretend it's a little straighter than what I'm able to do. Okay. Looking at that line, I want to find the magnitude so that it's 1. So in other words, what I can do is notice that if I were to draw the vector going straight out to that point, this vector would be represented by In vector format, what are my components? -3, 7, right? How can I take that vector and scale it down to have a magnitude of 1? What's our computation to do that? To form it into a unit vector, I take the vector itself and I divide it by its magnitude, which is going to be -3 squared plus 7 squared. So that gives me -3 over, what is 3 squared? 9 plus 7 squared is 49, so 9 plus 49 is, so I'm dividing by the square root of 58 on both of those components. Okay, so what this does is it gives me, it gives me the unit vector in this direction. If I can make it work, there we go. So this unit vector is given by this stuff down here. So what I want to do now is take that unit vector and just shift it back this way so that it lines up off of the point A, right? Because technically I'm supposed to be doing this so that it is a vector from A to P, not the origin to a point, right? So how do I take that vector and shift it? What do I add onto each of onto the components? 7 onto which component? The x. Do I have to add anything onto the y component? No, I don't, right? All right, so if I'm going to shift that guy back, and let me color coordinate this a little bit, then I'm going to be finding this vector. And this vector will be given by taking the vector that I just found, adding 7 onto that x coordinate, something doesn't seem right to me. Nope, I lied. That's fine. All right, adding 7 onto that x coordinate, and then, because we're supposed to be finding the point P, so should I be writing this as a vector form? That's what didn't seem right. I'm not supposed to be writing this as a vector, right? I'm supposed to be giving the point P, where P is going to be this point right here, yeah? So that's P, and then the y coordinate is 7 over the square root of 58. And just that, right? That's the y coordinate. Is that the only point P I could have found that would be perpendicular? What's the other one I could have found? Going in the negative direction. So I could have also done going in this direction, right? And I could have called this point P. It would still have a similar technique, wouldn't it? What's the only thing that would change? Instead of having a negative, instead of starting at a -3, whatever, it'd be a positive 3 over the square root of 58, and then we'd be adding 7 to that still. And then what would be different about the y? It would be a negative. So basically you just switch the signs on the x and the y of the original point. Are there any questions about how we got both of those p-values? Now, did I have to find both of them in this case, the way they phrased it? I didn't. They just said find a point P. So technically I could have stopped at 1, but I wanted to show you that technically there are 2. Are there any questions on this? No? Okay. There is your homework. This will be due tomorrow, so make sure that you're ready to do your corrections tomorrow. It's posted on Schoology. And then you'll have your quiz on Monday over 6.1 and 2.